In the previous lecture we were discussing about the heat conduction equation. So, we will write the heat conduction equation assuming that we are now interested for heat conduction within a solid only. So, rho Cp let us consider an example with Kx equal to Ky is equal to Kz is equal to K. So, then you can write this in compact vector calculus notation is known as, it can be written as Laplacian of t or del square of t, where del square is del square del x square plus del square del y square plus del square del z square. Now, as obvious, this form of the equation is valid for a Cartesian coordinate system. Now, you can express this form, this particular equation in terms of other coordinate systems like cylindrical polar coordinate system or spherical coordinate system. You just have to adopt the expression for del square in various coordinate systems. These are given in your textbook, and I am not trying to copy that material from the textbook to just waste time, but it is a very simple exercise that you from any engineering mathematics book or even in your heat transfer textbook you will find an expression for del square for the cylindrical and the spherical coordinate system, and you can substitute that here to get the equations in the various coordinate systems. Normally we expect that for problem solving you remember this particular form, but the spherical and the cylindrical polar form may not be easy to memorize and reproduce, and for exam purpose we are not going to test your memory. So, if those forms of equations are necessary, we will provide you with those forms. So, do not be bothered about remembering those forms as a part of your preparation for the exam. Now, as I told you that this equation is in terms of mathematics an initial boundary value problem. So, what kind of problem we are talking about? Let us say that there is a rectangular slab, just as an example, at time equal to 0 the temperature is some initial temperature which is say some atmospheric temperature, and then some temperature disturbance is applied at the boundary, and then the temperature of within this rectangular piece will change as a function of both position and time, right. So, you are applying some boundary conditions, based on the boundary condition only the temperature within the domain will change as a function of position and time. So, question is what types of boundary conditions are possible? So, the first type of boundary condition that we talk about is the most obvious one, where at some boundary we specify the value of temperature. we say this is the temperature is equal to say T0 at this boundary. So, T specified at the boundary. When temperature is specified at the boundary or the dependent variable in general is specified at the boundary, this in mathematics is called as Dirichlet boundary condition. Next possibility is that temperature is not specified at the boundary, but heat flux is specified at the boundary. Heat flux is specified means that gradient of T is specified, because heat flux is related to the gradient of temperature through the Fourier's law. So, gradient of T is specified at the boundary, this is called as Neumann boundary condition. A third possibility is that neither of temperature is specified or heat flux is specified, but one is expressed as a function of the other at the boundary, that is called as mixed boundary condition. So, grad T expressed as function of T, this is called as now we have to understand a very simple thing, or we have to answer a very simple thing. Can we give any boundary condition for any problem? Or is any boundary condition out of these three a valid boundary condition? That is something which will follow from the physics of the problem. I will give you an example. Let us take an example, example 1. Let us say you have a rod like this. This is a one dimensional problem. One dimensional problem means we are having temperature variation only along x, along y and z. It is very large, so there is very small temperature gradient. So, along mainly you have, or the temperature gradient is imposed along x. So, there is a temperature difference that is taking place as you are moving along x. So, whatever may be the reason, we say that T is a function of x only. So, if T is a function of x only and Q triple prime is equal to 0, there is no heat generation, then what is this equation? If T is a function of x only, this term is 0, T is not a function of time. So, you will get this term equal to 0, this term equal to 0 and this term equal to 0, and because T is a function of x only, you have not only this, the other consideration is k equal to constant, because if k is not a constant, it will not be d2t dx2 equal to 0, but ddx of k dt dx equal to 0 if k is not a constant. So, k is a constant is also an assumption. Let us say we want to solve this equation. This is very simple, elementary school level, not even high school level, but it is important that we look into this very carefully. Let us say that I tell you that at this point the heat flux is this, at this point the heat flux is, this is the heat flux direction, L is the length of the rod. What type of boundary condition we have given? Neumann type boundary condition, right. So, in a mathematician's language, this is a nicely defined problem because we have given two boundary conditions, valid boundary conditions at the two ends. Now, can you solve this equation? Let us say that this is 1 watt per meter square, let us say this is 2 watt per meter square given. See, this is where you have to bring your physical insight into mathematics. Mathematics is not about integration, differentiation and all. Always try to understand the physics of mathematics. That is how you can enjoy learning mathematics. So, look into this equation. So, when you look into this equation, you will see that here you have a heat flux which is 1. Here you have a heat flux which is 2. Now, the rate of heat in is different from the rate of heat that is going out. When is it possible? When there is some generation inside or there is some change with respect to time. But it is a steady state problem. So, if this term is 0, that is called as steady state problem. So, there is no change with respect to time. So, when there is no change with respect to time and there is no heat generation, whatever comes in, the same must go out. So, this is a physically inconsistent problem or an ill-posed problem, right. So, any boundary condition you give is not a valid boundary condition. Now, you may say that, well, I have understood it now, let me give this as 1 watt per meter square, right. Then it is physically consistent. Now, can you solve this problem? Let us quickly try to solve this problem. So, you have dt dx is equal to C1, right, integrating these ones. So, let us say that thermal conductivity of this solid is 1 watt per meter Kelvin, just to simplify the calculations. So, the heat flux at x equal to 0, you have minus k dt dx is equal to 1 watt per meter square. So, you will get what is dt dx. So, that means what is C1? This is minus 1 Kelvin per meter, because K is 1 watt per meter Kelvin, right. When you integrate this, you will get T equal to C1x plus C2, right. How will you get this C2? You cannot get this C2, right. So, this problem, so does it mean that this problem does not have a solution? No, this problem has infinitely large number of solutions. So, what are the possible solutions? So, if you plot t as a function of x, so it is a family of straight lines with a slope of minus 1 Kelvin per meter. So, it could be this, it could be this, all parallel ones. Infinite such possible straight lines with same slope, but intercepts are different. But if you are practically measuring temperature in a problem, then at a given point the temperature cannot be infinite number of possible values. It will be a unique temperature, right. If you put a thermometer or a thermocouple in a physical body, you will get a unique temperature. That means this is not a well posed boundary value problem. So, mathematically these are called as ill posed problems. So, at least at one boundary you must specify the temperature for this steady state problem. Otherwise, you will not be able to identify which of these straight lines your solution is. So, the moral of the story is any condition given at the boundary is not a valid boundary condition. You have to apply your physical judgment before giving the appropriate boundary condition. So we have discussed about the Dirichlet-Neumann. The third point that we will discuss about, what is a mixed boundary condition, how does it physically come, before attempting to solve 1, 2 or 3 simple problems, and then we will call it a day. So now let us take an example again. Let us say that you have a rod like this, wind is blowing with a velocity, some velocity, so that this end of the rod loses heat to the ambient by convection. Let us say that the convective heat transfer coefficient is H and the temperature is T infinity, ambient temperature is T infinity, okay. So H is the convective heat transfer coefficient and the ambient temperature is T infinity. So what is the boundary condition here? The boundary condition here is that whatever heat flux reaches here by conduction, the same heat flux gets left from here by convection. So what heat flux reaches here by conduction? That is minus k del T del x. Let us say this is x equal to L, is equal to what heat flux leaves here due to convection, and if you in addition take into account radiation, then for a gray surface right, where sigma is the Stephan-Boltzmann constant and epsilon is the emissivity. So because this particular MOOC course is basically on emphasizing on conduction and convection, for the time being we will not consider this term, but you should keep in mind that if radiation is there, this term is important, and for not all practical problems radiation is important. You can see that the radiation is important only when this temperature difference is very large, because it deals with the 4th powers of the absolute temperature difference. So if radiation is not important, then you can write this as minus k del T del x at L is equal to H into T minus T infinity. So this is what? Temperature gradient expressed as a function of temperature. So this is called as mixed boundary condition. Now where is the fluid mechanics coupled with this problem? The fluid mechanics is coupled with this problem because you have to understand what is the value of H. You cannot just say let us assume H equal to 1, 200 like that. It will come from the basic fluid mechanics. And how does H come from basic fluid mechanics? That will be our agenda for studying convection. For the time being, while solving the conduction problems, for taking this as a boundary condition we will assume some value of H. But how does the value of H come? Does it come by magic? Does it come by intuition? Or does it come from fundamental fluid mechanics? That answer we will give when we discuss about convection. So this is a mixed type of boundary condition. Now let me ask you another question. Let us say that instead of a steady state problem, this is an unsteady state problem. So far like that problem we are considering a steady state problem. But let us say it is an unsteady state problem. Can we use the same boundary condition for an unsteady state problem? That means temperature, unsteady state problem you understand, right? Temperature also varies with time. Can we use this same boundary condition for an unsteady state problem also? Because what condition we have used? That whatever heat rate at which heat has come here, at the same rate heat has left. Can we use the same condition even for unsteady heat transfer? That is my question. Yes or no? So these days all of you are habituated with multiple choice answers. So let me give 4 answers: yes, no, maybe, the third one I do not know, the fourth one. So what will be the answer? You have followed my question, right? So we have used this for a steady state. Can you use this for an unsteady state also? Answer is yes. We can use it for an unsteady state also. Why? The reason? The reason is that this is what? This is a surface. Surface cannot store any thermal energy. Thermal energy can only be stored by a volume. So the rate at which heat has come here, at that instant, at the same rate heat should leave, because it is at the end a surface which cannot store thermal energy, no matter whether it is steady or unsteady state. But if it is not heat transfer but electrostatics, it is not the same thing, because a surface cannot store thermal energy but a surface can store electrical charge, right. So like throughout this course I will try to give you analogy between one with the other, because engineering at the end is like basic applied physics, chemistry, mathematics, and all the branches of engineering are somehow interrelated by very unique mathematics. And if you develop that kind of insight, you can relate practical problems with the mathematics that you learn. So this is valid even for unsteady state. The next point is that if you write this del T, take the rho Cp here, then you can write this as k by rho Cp del square T plus q triple prime by rho Cp. This is what is alpha, the thermal diffusivity. So as I told you, the value of k itself is not that important, but k by rho Cp is more important, right. From mathematics it follows in this way, but how do you physically interpret it? See, what represents k, or k represents what physical attribute? K represents the ability to conduct thermal energy, and rho into C is what? It is like the specific heat. It represents the ability to store thermal energy. So it is the relative ability of conducting energy with respect to storing energy. That is what is important, not the absolute value of conductivity, but the relative ability to conduct with respect to the ability to store. What is the unit of this? This unit is meter square per second. So, and again the analogy, in fluid mechanics, what is the equivalent parameter? Kinematic viscosity. So kinematic viscosity is also the ability to transmit momentum disturbance divided by the ability to sustain momentum disturbance, sustain momentum. Okay. Now for a solid, it does not matter whether it is Cp, Cv or what, because for solid Cp and Cv are the same. So very commonly for solids you write this as C instead of Cp or Cv, because for solids, because compressibility effect is not there, Cp, Cv, C all are same specific heat. So the equation, normally in mathematics books you will find that this term is often not considered. So this equation is represented as heat equation. You must have studied heat equation in partial differential equation in mathematics, and that is this equation. Okay. Now we will work out a few problems. All the problems that I will be working out today are from the exercise problems of Impropera's book, which is one of your textbooks. So I am not giving the problem number because you might be having books of different editions where the problem number might change. So I will better discuss about the problem, and you can identify the problem number if you are interested by looking into the exercise of the book. So let us say that there is an infinite medium, this is a problem. So there is an infinite body in which the temperature is given as a function of x, y, z. Find the regions where temperature changes with time. So we will assume that there is no heat generation. So let us calculate what is del square T, because temperature dependence on time is governed by this equation. So if we calculate the right hand side, we can get the left hand side. So the first derivative, let us so if you add right, that means you must have. So what is the answer? There is no region where temperature changes with time, right. What are the assumptions that we have made for solving this problem? No heat generation, constant thermal conductivity. These two are the major assumptions that we have taken. Next problem. So, you have a one dimensional problem where the boundaries are given, the boundary temperatures are given, and temperature within the slab is also given as a function of x. So, the first part is find the surface heat flux. So, basically you use the Fourier's law, the heat flux. So, here T is a function of x only, so minus k dt dx. I am just outlining the solution and you can plug in the numerical values, I will give the final answer, you can check. So, what is the heat flux at x equal to 0? This is minus k dt dx at x equal to 0. So, you find out dt dx, t as a function of x is given, and then find out minus k dt dx, substitute x equal to 0. So, this answer is 200 watt per meter square. What is this is 182 watt per meter square. So, what is the rate of change of wall storage? Is basically the difference. So, this is what is entering, this is what is leaving, the difference is the change. So, this is 18 watt per meter square. So, this is an unsteady situation when there is a wall storage. So, it is better not to write this, I have written by mistake because I thought it is a steady state problem. So, do not write it as dt dx, but write it as del t del x, just for fundamental reasons. Okay. The third is you can write what type of boundary condition it is, mixed type of boundary condition. So, from here you can find out what is H. It is 4.3 watt per meter square Kelvin. So, you can check by substituting in this equation that you will get a del t term. This right hand side will not be equal to 0. So, temperature at a given point will change with time. Okay. Depending on whether it is positive or negative, temperature at a given point will increase with time or decrease with time, that will come from the calculations. We will work out one final problem from this chapter. Now, before working out the final problem, I will try to bring out a relatively apparent but paradoxical situation concerning the previous problem. So, you might argue that temperature is given only as a function of x, but how can you say that temperature depends on time, right? And this problem I have not created, this problem is from an established textbook, and there is a reason behind this. It is actually a valid situation. What it quotes is, at a given instant of time it gives temperature as a function of x, right. So, at a given instant of time it gives temperature as a function of x. So, that temperature as a function of x does not include the time because it is at a given instant of time. So, at a specific instant of time you will have, say, say there was time within the expression, but say time equal to 1 second has been substituted. So once it has been substituted, the time is not appearing. So that temperature as a function of x is at a given instant of time. So that will resolve the paradox, because it will be kind of apparent that why it is so, that temperature is a function of time we are seeing, but it does not appear in the expression of T, it appears as a function of x only. So the final problem, so this is a very practical problem where there is a material and laser is falling on the material. It may be used for various reasons, starting from manufacturing to medical treatment, whatever may be the reason, but laser is falling on the material and the temperature is exponentially decaying. So the temperature is maximum at the location where the laser is falling, and as you move along x, the temperature is decreasing exponentially. So it is an attenuation as a function of x, k is the thermal conductivity, a, b, c are some constants. Now when the laser is falling on the material is absorbing a part of the energy given by the laser, and that gives rise to the change within the material. It may be a biological change, for manufacturing it can be a microstructural change. So it is very important to find out the rate of energy absorption within the material. So how will you do that? There are many ways of solving this problem, but because we have derived the heat conduction equation today, we will use the heat conduction equation to solve this problem. So we will make some assumptions. Constant thermal conductivity and one dimensional steady state. Okay. So the equation will boil down to 0 right. So because t is given as a function of x, from here you can find out what is q triple prime. This will be what? This will be a function of x, right. So what is the rate of energy absorption? Where L is, so L is the length along x of the material. Okay. So you integrate this over the length, actually you integrate it over volume, but one dimensional problem, length is replacing the volume because the area in the other direction is infinitely large. So basically you are, this is a representative of the length, representative of the volume, but for a one dimensional case any change is taking place along the length only, the cross sectional area is not of importance. So that is why we integrate it over the length from 0 to L, and let me give you the final expression. So let us summarize what we have learned today. We have learned first how to physically perceive energy balance, then how to express the different terms in energy balance mathematically, how to express that in the form of a differential equation that involves temperature as a function of position and time, how to prescribe the boundary conditions, and what are the possible and feasible ways of giving boundary conditions and what are their physical implications. This is all what we have studied today. Now in the next lecture you will be introduced basically one dimensional steady state heat conduction problems. That will be a special case of this equation where this term will be 0 and this term will have only one component of the derivative, that is derivative along x, derivative along y and z will not be there. So these one dimensional problems and their applications in engineering will be covered by Professor Shom, and then we will discuss, I will come back to discuss about the two dimensional and unsteady state problems. Thank you very much.